Previously, I explained global histogram, or rather global thresholding. Okay, using a global threshold, basic global thresholding actually. And we did that by finding a threshold in an automatic way. And I also talked about when does this method fails. It fails especially when we have an object that represents a very small percentage of the entire image, or vice versa. Okay, so now what I want to talk about is global optimal thresholding. Okay, global optimal thresholding. Now, what I mean by this term optimal. In the past, I talked about basic global thresholding. Now, I'm talking about the optimal thresholding. Well, this optimal thresholding is just a threshold. Okay, let's denote it T optimal, that minimizes the error. So it minimizes the classification error. So if we have histograms like the ones I exposed in the previous video for the basic global threshold, and then this optimal thresholding may not really matter. So if we have a histogram like this one, where we have a clear valley, okay, between the two distributions, then finding this is not really important. But in some cases, we need to find that threshold. So let's say that I have, for example, a histogram like this one, okay, and it can be considered as a mixture of two distributions that are overlapping with each other. Okay, let me highlight that to see it in more details. So this is the first distribution, okay, and this is the second distribution, and they are overlapping in this interval. Let's call it AB. Okay, so first of all, let me talk about why does this situation happen. So there are many reasons. For example, it can happen if I have an object that has the same color as the background, and as a result I get an overlapping. Another case where this can happen is uneven illumination. So let's say, for example, that I have an image, okay, that has some writing on it. Let's say that this image represents just a piece of paper that has some writing on it, and because the illumination is uneven, so I have here, let's say in this region here, a very high illumination, and in this other half, a very dark illumination, or very weak illumination. And as a result, I'm gonna get here some shadings in black. So in this case I have shadings, or dark shadings, okay, of the background, and I also have dark words. These words, or this text, dark text, that has also a dark color. So because of the uneven illumination, we get overlapping histograms. Now this is explained, so this is just an intuitive explanation. There is actually a mathematical explanation for that, and in order to understand it, we have to consider that we have to know that the image, okay, any image xy is considered as the multiplication, this is the model of the image, the multiplication of x reflectance by the illumination. So it can be, an image can be modeled with two components. The first component is the reflectance, and the second component is the illumination. And in order to get that image, we have just to multiply these two components. Now the reflectance is just how much of light is reflected at the point xy. And the illumination is just how much of light is sent at the point xy. Okay, and if we visualize the histogram of this reflectance component, we can find that it is unimodal. Okay, and the same thing for the illumination, it is also unimodal. Okay, and there is a probability theory that says, well, if I have the histogram of this one and this one, then the histogram of this one is just a convolution of these two histograms. It's just a convolution of this one and this one. Okay, so this is roughly what this theory says, and the convolution operation is known to merge two signals or two functions. For example, if I have a signal like this one, triangular, and a signal like this one, which is rectangular, then the convolution in some cases would lead to this signal. We just merge the properties of this rectangle along with the property of this triangle along with the properties of this rectangle. So this is the convolution operation. Okay, and as a result, if we convolve this one, this curve and this curve, we are gonna get something that is convoluted like this. Okay, this was just a mathematical explanation of why we get such a distribution. Okay, now the problem with that distribution is that a global thresholding would lead to an error, no matter what value we take for that threshold. Okay, and to illustrate that more, why this is the case, let me just draw this bimodal distribution on another paper. So this is my bimodal distribution that is convoluted, merged, or overlapped. Okay, so this can be, so this is PZ, let me call this PZ. This is the axis PZ, Z. So Z just represents the intensity level of the image, and let's say that it's maximum at 1. Okay, so now we consider that this function, or this probability distribution function, is a mixture of two other distributions, which is this one, P1Z, and this one, P2Z. Okay, and if I were to draw this on individually, I would get this function. I'm also going to draw this individually, and this is what I'm going to get. And I'm going to explain in a minute why I'm drawing them independently. So let's say that I take a threshold here. So this threshold would be here for this distribution, and its projection on the other distribution would be here. Okay, so no matter where I move this, this threshold, I'm always gonna get an error because this distribution is overlapping with this distribution, so they do not have a clear valley. So in this case, this would be the error. So this P1Z is associated with the object, okay, and this P2Z is associated with the background, let's say. This is our assumption. So in this case, we would get this percentage of object pixels as misclassified as the background. And this percentage of background pixels misclassified as object pixels. So now the problem is we need to find a threshold such that the sum of this error, the total error of percentage of misclassified pixels is minimum. So I'm going to discuss two methods for that, or two techniques for that. The first is analytical, okay, the two techniques, and there are more, of course, but these are the most used ones, especially Otsu technique, that I'm going to also explain. So the first technique is analytical technique. And the reason why it is called analytical is because we try to estimate that error, okay, the total error of misclassified pixels mathematically. And it is expressed in terms of threshold because it depends upon the threshold, okay? So we try to find mathematical expression and then minimize it. This is the first technique. The second is called Otsu method, which is, as far as I know, the most used to establish a global optimal threshold. And one of the reasons is because it's simple, and this analytical method is very complicated and it may be heavy in computation. Okay, so I'm going to discuss these two techniques in the previous videos.